All right, so in our previous videos, we've set up things with the energy level diagram for a hydrogen atom, and we've talked about the difference between a ground and an excited state electron. One of the things that we talked about also was that when an electron is excited, it almost certainly is going to make its way back to the ground state. And that may happen in one big jump, or it may take several jumps along the way. So, for instance, in this particular diagram, we see an electron in a hydrogen atom that is in the third shell or the third orbit. If it jumps back down to a lower orbit, we would say that it is relaxing. So, a relaxation process is when an electron transitions from a higher energy orbit to a lower energy orbit. We can write that. The typical transition like this one might be written such as n equals 3 goes to n equals 2. And I know that that is a relaxation process because the electron's going from higher energy to lower energy. When it does so, it has to get rid of energy in that process. And if you notice in the n equals 3 level, it has 13.1 electron volts worth of energy. The n equals 2 electron orbit has 11.2 electron volts. So if an electron is going to relax from the third state to the second state, it has to lose a total of 1.9 electron volts. Now that may not mean anything to you. However, we can find the equivalent number of joules that 1.9 electron volts is. And I've done that already. 1.9 electron volts is the same thing as 3.04 times 10 to the minus 19 joules. And just to be clear, this is the amount of energy that an electron has to lose in order to make the transition from the third state to the second state. It can lose that in the form of light. So what we're going to do is a quick calculation where we figure out exactly how much energy or exactly what wavelength of light is released when that transition takes place. Let me show you how we would do that. We learned an equation the other day that E is equal to 8 times frequency. But we said an equivalent equation would be E equals hc over lambda. And this is the one I want to use because it can let me solve for wavelength. So if I rearrange this equation, I get wavelength equals hc over E. And in this particular case, that means I have 6.626, that's Planck's constant, times 10 to the minus 34 joule seconds times the speed of light, 3 times 10 meters per second, divided by the energy, which is 3.04 joules. If I cancel units here, joules cancel out, seconds cancel out, and I'm left with meters. And that comes out to 6.54 times 10 to the minus 7 meters, which is also known as 654 nanometers. That's the wavelength of light that is emitted when an electron relaxes from n equals 3 to n equals 2. If you look in our line spectra, that's this line right here. It says 656, close enough. And we know for certain now that when an electron jumps from n equals 3 to this wavelength of light is given off. We could actually do that for all four of the lines in this line spectrum, and this is what we would find. This line right here, light blue, is n equals 4 to n equals 2. This one is 5 to 2, and this one is 6 to 2. And it begs the question, why don't we see any of the transitions all the way down to the ground state? In other words, why am I not seeing in my line spectra this transition all the way down to n equals 1? Where did it go? Well, the answer is pretty simple. It's too high in energy for us to see. And almost certainly we would see this if we could see if we could see um, ultraviolet light, but we can't. So the big jumps all the way down to the ground state are more likely to represent ultraviolet jumps, whereas you could even have low energy jumps like n equals 5 to n equals 4, which we also can't see, which might be represented by an infrared jump, which is lower in energy than visible light is. Okay, we'll spend some more time in class on this tomorrow. Thanks for listening. We'll see you next time.